Hello, in this video I'd like to talk about how we can apply EF games to other sorts of structures. In the previous video I specified that EF games would only work on structures that had a finite number of relations to them and no operations. And we saw just how powerful EF games could be, eventually being able to completely classify the non-standard models of the natural numbers as a linear ordering, and provide a complete axiomatization for this class of structure. It would be nice to do the same thing for the natural numbers with a successor operation to them, but the successor operation is an operation, and so we can't directly apply the notion of EF game to it and know that it will tell us the things that we want to know. So first I'd like to talk a little bit about successor structures in general to try to anticipate what sorts of results we might get when we analyze this specific successor structure. First of all, a successor operation is less expressive than an ordering. If we have the ability to talk about orderings, we necessarily have the ability to talk about successors. If we want to express that y is the successor of x, all we need to do is say that y is greater than x and there's no element between y and x. So if we're working in a language that has the ability to talk about ordering, then we automatically get the ability to talk about successors when they exist. Note that not all orderings are going to have successor operations to them. For instance, the real numbers as a linear ordering, it's not the case that there's ever going to be an element that's immediately larger than another element with no elements in between. But when these successor elements do exist, we can talk about them in the language of ordering. On the other hand, if we want to talk about ordering in the language of successor, we can't really do that. We might want to say that y is greater than x means that there's some number of successor operations that we could apply to x in order to get y. But first of all, first-order logic does not allow this sort of construction. Every formula in first-order logic has to be a concrete formula, and this formula here is not concrete in its length. Additionally, this sort of formula here doesn't handle the case where y is infinitely far away from x. We can imagine a situation like omega plus omega star, where we have two elements that have infinitely many elements in between them, and so there isn't going to be a sequence of successor operations that we can apply to one element to get another element that's infinitely far away from it, even though that element is going to be larger. So we can't really talk about ordering in terms of successor. Because the successor operation is less expressive than ordering, we expect potentially more non-standard models. Remember that non-standard models have to satisfy all of the formulas that the original structure satisfies. And so if the number of formulas decreases, right, if the amount of stuff that we can express decreases, then the amount of things that we require these non-standard models to satisfy also decreases. And with fewer constraints on the non-standard models, there's more flexibility for those non-standard models. We wind up potentially getting more non-standard models. Fewer constraints means more possibilities. Additionally, since our equivalence for successor involves this quantifier here, whenever we need this quantifier as part of our formula, we get it for free when we talk about successors. So for instance, if we wanted to talk about every element having a predecessor, well, we could do that with one fewer quantifier because we're saving specifically this quantifier when we talk about successors. So we expect that some formulas that are specifically related to the notion of successoring to have fewer quantifiers in them. On the other hand, because successor is less expressive, we expect some formulas to require many, many more quantifiers, or potentially not be expressible at all. I'd like to use Ehrenfeucht-Fraïssé games to demonstrate these results formally, but how can we talk about Ehrenfeucht-Fraïssé games on a structure with an operation? Well, the simplest way is to relationalize our structure. We want to take our formulas, and where we see y is equal to the successor of x, we want to think about that as saying that some relationship holds between x and y, and this is really a structure that's talking about this particular relation here. This sort of translation doesn't add or lose anything from our language. Anytime that we have something like r of xy showing up in a formula, we can of course translate it into y is equal to the successor of x. And every time we have a more complicated formula, like y is the successor of the successor of the successor of x, well, we need to break this apart into just pieces that look like this so we can translate it into the language of this relation here. And we can do that by adding some extra variables. We can translate this into saying that there exists intermediate variables w and z, such that y is the successor of w, and w is the successor of z, and z is the successor of x. And then we can translate it to being written in terms of this relation here. So any formula that we can write like this can be translated into the language of this particular relation. We need to be a little bit careful because atomic formulas in the language of the successor can actually look like the successor of the successor of y is equal to the successor of the successor of the successor of x. We could be applying the successor operation to terms on both sides of the equality, but generally speaking, this is all we can do with atomic formulas, and we need to handle this case either by saying, oh, there exists a separate variable z, such that this is equal to z and z is equal to this, or we need to take advantage of the fact that the successor operation is invertible to turn this into just y is equal to the successor of x, depending on whether or not we have that. Ultimately, this isn't such a big deal, but it will throw off the counts of quantifiers if we take that first option. But notably, switching from a successor structure to a relationalized version of that structure throws off the quantifier count anyway. We took here an atomic formula that had no quantifiers in it, and we wound up having to translate it into a formula that had 2 quantifiers in it. So even though we can translate freely back and forth between the successor structure and the relationalized version, that translation does not preserve quantifier depth. And so if we want to reason about quantifier depth, then we need to do something else. And I'll talk about that something else later on in the video. For now, though, remember that we aren't so much concerned about quantifier depth. The ultimate results in terms of axiomatizations and non-standard models that we got in the previous video using Ehrenfeucht-Fraïssé games didn't have anything to do with quantifier depth. So we don't need to worry too much. But it is worth noting that when we relationalize, quantifier depth winds up reflecting a combination of the quantifier depth of the original formula and then also some nesting of the successor operation, and it will also kind of count if there's successor operations being applied on the left and right. So we're all set. We're ready to play Ehrenfeucht-Fraïssé games on successor structures. All we have to do is relationalize them and then make sure that the moves within the Ehrenfeucht-Fraïssé game respect this particular relation here. That is the y being the successor of x relation. And in fact, for clarity, I'm just going to write this relation as y is equal to the successor of x. Because when I look at r of xy, it's not clear which one is the successor of which, or even that this has anything to do with successors at all. So I'm going to use this as shorthand for this. Let's take a look at the Ehrenfeucht-Fraïssé games on some finite structures with a modular arithmetic-based successor operation. Again, we will use 3 to represent the set 0, 1, 2, and we'll use 2 to represent the set 0, 1. These are somehow the canonical sets of those size. And the modular successor operation on this set takes 0 to 1, 1 to 2, and then 2 back to 0. And then the modular successor operation on this set takes 0 to 1 and 1 back to 0. Let's say that spoiler starts by playing at this 0 here within n, and duplicator matches it to this 2 within m. Now let's say that spoiler plays here at this 0 in m. Now, because x2 is the successor of x1, y2 needs to be the successor of y1. And the game is actually over at this point. There's an atomic formula satisfied by one of the assignments that isn't satisfied by the other. Can you find it? So in addition to y2 being the successor of y1, y1 is also the successor of y2. Right? The successor of 1, because this is modular, this wraps around, the successor of 1 is 0. On the other hand, in this structure, the corresponding formula is not true. It's not the case that x1 is the successor of x2. So we have an atomic formula that's true in this structure that's not true in this structure, and so duplicator has lost. These sorts of loop structures are really important, and we'll come back to them later in this video, but they're tricky to work with. So I'm actually going to take advantage of the fact that we've relationalized and get rid of these relationships. Normally it's considered polite when you're defining a structure that has an operation on it to make sure that that operation is closed. We don't want to have to worry about writing out terms that might not refer to elements of your structure, because, for instance, there might be something that you can't take the successor of, and we might accidentally have a formula like s of x, and x might refer to 1 incidentally, and s of x then is a meaningless formula. But fortunately, we're already thinking about these structures in a relationalized way, and it's perfectly okay for a given x for there not to be any y such that r of xy. So we can simplify our reasoning for ourselves by just focusing on the structures that have a finite number of elements and a successor operation that it might not be closed under. Again, thinking about these things in a relationalized way so we can actually play the EF games. Before we analyze this game here, I'd actually like to talk about how we deal with constants in EF games. So let's say we start out with the very basic, the integers with a successor operation, but then we add two distinguished constants. I'm going to call them a and b, and write them in that order in the specification of the structure. For the first structure, a is going to represent 0 and b is going to represent 3, and in the second structure, a is going to represent 3 and b is going to represent 0. If we were dealing with the ordering structure for these two, the Ehrenfeucht-Fraïssé game would already be over before it starts. There's already an atomic formula that's true of one structure that isn't true of the other. In particular, for this structure, a is less than or equal to b, and in this structure, that's not true. So without having to take any turns into the game at all, there's already an atomic formula differentiating the two structures. In other words, duplicator loses right away. Let's take a look at what that looks like for the actual game. Whenever we have distinguished constants in these two structures that are supposed to correspond to each other in terms of how we use the language to talk about them, we want to imagine that those constants are already matched with each other. So here, the constants for A should get matched to each other, and the constants for B should also get matched to each other. That is, that we start the game off with some matchings already available. This is actually really useful if we want to analyze games that are already in progress. But let's take a look at how this game is played on these successor structures. So again, we still have this matchup, but we no longer have an atomic formula that's true of one structure that's false of the other. The only sorts of atomic formulas that we can have on these relationalized successor structures, I haven't indicated that, but if we're playing an Ehrenfeucht-Fraïssé game, everything has to be relations. So if we're looking at atomic formulas, well, we don't have any variables yet because we haven't actually started the game, but we can talk about constant symbols A and B. We can say, for instance, that A equals B, which isn't true, or we could also say that A is the successor of B, or B is the successor of A, which isn't true in either of these structures. So the game isn't lost yet. There's no atomic relation between these two elements, and there's no atomic relation between these two elements, and so every atomic relation that holds of the elements already picked up here also holds of the elements already picked down here. So what can spoiler do? Well, let's say that spoiler plays at this one up here. Now these two elements are related, right? This one here is the successor of 0, the successor of A. And so in order to preserve the fact that X is the successor of A, duplicator needs to match this to an element which is the successor of A in this structure here. Duplicator needs to preserve this successor relation when they do their matching. Let's say that spoiler then plays at 5 in N, then because 5 is the successor of 4, duplicator must match it to 2 in this original structure, and the game is actually lost here. In this first structure, we have the atomic formula that B is equal to the successor of x2, right? 3 is the successor of 2, but the things that they got matched to are not related in that way. It's not the case that down in this structure, B is the successor of y2, right? Because 0 is not the successor of 5. And so we have an atomic formula that's true of this structure up here that's not true of this structure down here, and so the game is lost. This sort of analysis formalizes our intuition that there are some sorts of distinctions that we can make right away in our ordering structures that we require a few quantifiers in order to make in our relationalized successor structures. Let's suppose now that we're playing an Ehrenfeucht-Fraïssé game on the integers followed by a copy of the integers as an ordering with distinguished elements for the central point of each of these copies of the integers. Let's think of these constants as A and B. Again, we want to imagine these constants as already being matched up. So matching up the values of A and matching up the values of B. Again, if we're thinking about this in terms of the linear orderings, the game is already over. We can express the difference between these structures as an atomic formula, the question of whether or not A is less than or equal to B. On the other hand, if we think about these as successor structures, I'll let you think for a moment. What is spoiler's strategy? What is duplicator's strategy on this particular game here? Well, suppose that spoiler plays here. Then duplicator necessarily has to play here. On the other hand, if spoiler plays somewhere like here, duplicator is going to want to play at C+2? Not because they have to right now. There's no relationship in this structure between 0 and 2. Right? Again, this is the relationalized structure, so we can only say that y is the successor of x. We can't talk about successor of successor yet. We need to actually use the quantifiers. We actually need to use steps in the Ehrenfeucht-Fraïssé game to describe relationships like that. So there's no atomic relationship between 0 and 2. Nonetheless, if duplicator matches this 2 here with C+2 up here, they've set up for in case spoiler plays at this 1 or this C+1 that they can match it and keep everything going. And as long as duplicator is careful to match up elements of this half with corresponding elements of this half and elements of this half with corresponding elements of this half, duplicator can play forever. In other words, duplicator has a winning strategy on the Ehrenfeucht-Fraïssé game of length n for every n. In other words, there's no formula in the relationalized version of these successor structures distinguishing them, and therefore there's no formula in the original successor structures that distinguishes them. Because if there were a formula in the original successor structures, we could turn it into an equivalent formula in the relationalized structures that we're actually looking at. This formalizes our notion that we've genuinely lost something, going from orderings to successor structures. A set of structures that we were able to distinguish before is no longer distinguishable. Let's go back to our finite relationalized successor structures. And again, it's only because we did that relationalizing that we can actually get away with the successor operation not being closed, right? There isn't a successor of 1 in this structure here, and there isn't a successor of 2 in this structure here, but that's perfectly fine because we're thinking about them as relations. I'll let you analyze this game on your own if you want. How quickly can spoiler win? How long can duplicator last? If spoiler can force a win, what formula that distinguishes these two structures are they taking advantage of? So it turns out, rather surprisingly, that spoiler's winning strategy on these structures winds up being exactly the same as when they were orderings. Spoiler starts out by playing at this one here within n, and duplicator can either match it to 0 or 1 within m. But spoiler's really taking advantage of the fact that there's an element here that has both a successor and a predecessor, an element whose successor is it, an inverse image under the successor operation. Whereas these elements, this element doesn't have a successor, and this element doesn't have a predecessor. So regardless of which one duplicator matches this one up to, there's going to be some feature that's missing that spoiler can exploit. Let's say that duplicator matches it to this 0 here, then spoiler can play at this 0 here and exploit the fact that this 0 here doesn't have a predecessor in this structure. In this case, we can write the formula for what spoiler is exploiting as such. There is some element in the second structure such that it has both a successor and a predecessor. And again, when I write this, you should think of it as shorthand for R of x, y, that we're actually working in a relationalized version of this successor structure, but I want to write it this way so that it's clear what's going on. So this is what's happening in n, and we take the negation, no matter where duplicator matches this original x to, it's either going to be the case that every y is not the successor of x. In other words, duplicator matched to this one, and every y is not the successor of x, or duplicator matched to 0, like they did, and every y is not the predecessor of x. And again, we see this and/or duality indicating that spoiler has to respond differently depending on how duplicator plays. So again, by analyzing these games, you can see that duplicator easily lasts one turn, and duplicator can be forced to lose in 2 turns. So every formula of quantifier depth 1 that's true of m is true of n, and vice versa. But again, we have these formulas here, which are of quantifier depth 2, that distinguish these two structures. Right? This formula here is true of n, but not true of m. It turns out the situation is not quite the same between these two cases. Let's let m be the 3-point relationalized successor structure and n be the 4-point relationalized successor structure. If these were linear orderings, then because 3 and 4 are both greater than or equal to 2 to the n minus 1 for n equals 2, we wouldn't be able to distinguish these two linear orderings in 2 turns. However, as relationalized successor structures, we can distinguish them in 2 turns. Spoiler starts by playing here, and duplicator can match this point to, if duplicator matches it here, then spoiler plays here, and duplicator loses. if duplicator matches here, then spoiler plays here, and duplicator loses. On the other hand, if duplicator matches to 1, then spoiler can play here, and actually duplicator can't play in either of these positions, because this element is neither the successor nor predecessor of this element, but this element is the successor, and this element is the predecessor. So duplicator can't match to either of those two elements. And similarly, if duplicator matches this initial 1 to this 2 here, then spoiler can play at this 0 and win for exactly the same reason. It's a little bit complicated, but we can write out this strategy as a pair of formulas distinguishing these two structures. In the top linear ordering, there exists a place that spoiler can play so that no matter where duplicator matches it to, in case duplicator matches this 1 to this 0, in this structure, this element here is not going to have a predecessor, and in this structure, this element will have a predecessor. Or duplicator can match to here, in which case this element will have a successor and this element will not have a successor. And then in the case where duplicator matches this point to one of these 2 points, spoiler is going to want to take advantage of the fact that in this structure there's an element which is neither a predecessor nor a successor of the original element. Whereas in this structure, any element that duplicator matches it to is either going to be a successor or predecessor of the original element. Now, spoiler is going to need all 3 of these to be true for the particular x that spoiler picks in order to be able to respond correctly depending on how duplicator plays on their first turn. On the other hand, depending on how duplicator plays, depending on which x they wind up picking, one of these 3 is going to be true, and so we connect them with ORs. And so here's the difference between the top structure and the bottom structure, written out as a formula that's true of the top structure and a formula that's true of the bottom structure. And they're negations of each other. So as we can see, the situation is close to, but not quite the same as, the linear ordering case. And what's actually going on is that when a connection is made in the linear ordering case, the game splits into 2 parts. This part here and this part here. But when we're playing on the successor structure, the game still splits into 2 parts. Whenever a match is made, stuff that happens on this side of the match can't affect stuff that happens on this side of the match. There's no relationship between elements over here and elements over here. But we are going to want to keep this match as part of the structure. For instance, if spoiler played here, duplicator wouldn't be allowed to play at either of these 2 points. Duplicator would be forced to play here, because we already have these points matched up, and so therefore these points need to be matched as the successor of those points. So instead of reducing the game down to a 1-point versus 2-point structure, it's actually reducing the game down to this structure here, a 2-point versus a 3-point structure, where the initial points have already been matched together. Similarly, this also splits it up. The left-hand side board is going to be this. But of course, these 2 structures are isomorphic. This here is the 2-point relationalized successor structure. with a constant indicating the second of the 2 points, and this is exactly the same thing, a 2-point relationalized successor structure with a constant indicating the second of the 2 points. And so the recursion is slightly different for the case of relationalized successor structures than it is for just linear orderings. Nonetheless, a similar theorem is true to last time that we can exploit in order to look at non-standard models of the natural numbers as a successor structure. So I'm pretty sure this is correct. I've checked it computationally, and I've worked out a sketch of a proof that finite relationalized successor structures up to size 2 to the n are distinguishable by EF games of n turns, and finite relationalized successor structures of size 2 to the n and larger are indistinguishable from each other. So we get kind of 1 point more of distinction that we can make in the successor structure case than in the linear ordering case. And the proof by induction is actually kind of tricky because as subcases, you also have to prove this for finite relationalized successor structures whose first elements are distinguished by a constant symbol and whose last elements are distinguished by a constant symbol, and finite relationalized successor structures whose first and last elements are distinguished by constant symbols. The induction gets just that little bit more complicated. And also, just like before, we get that these large finite relationalized successor structures are also indistinguishable from the linear ordering omega followed by some number of copies of z, the integers, followed by a copy of the reverse of omega, the reverse natural numbers, the negative natural numbers. This structure is a linear ordering where if an element has an element after it, then it has an immediate successor, and if an element has an element before it, then it has an immediate predecessor. So we can make sense of the notion of successor for this structure, but this really isn't the way that we should be thinking about this structure. Within this linear ordering, elements of the omega part, or any of the integer parts, or the omega star part are all going to be infinitely far away from each other. And remember that the notion of successor cannot connect. It can only connect points that are finitely far away from each other. It cannot connect points that are infinitely far away from each other. And so these different pieces, the initial omega piece, various integer pieces, and the omega star piece, we should actually think of these as floating off in the void, unconnected from each other. There's no atomic relationship connecting these elements to these elements to these elements to these elements. Whereas in the linear ordering case, we could still compare them. We could still tell which one was larger than which. But in the successor case, there's no connection. So it might help to think of these as set theoretic unions. We also don't care about the ordering for the different integer parts. We should think of this as just an arbitrary set. And again, the induction for this proof is a little bit of a nuisance because you have to separately handle what happens when certain elements are already matched up to each other. You have to treat them as constants that have been matched together at the start of an EF game when you're doing the induction. So now let's try to construct non-standard models of the natural numbers as a relationalized successor structure. These will be the same as non-standard models of the natural numbers as just a regular successor structure because these two languages are expressively equivalent. I first propose a series of axioms for this particular structure. First, that the structure is closed under successor. Next, that every element except 0 has a predecessor. This predecessor is unique. And finally, there are no loops of size n for any n. This last is actually an infinite series of axioms. But it's really important to have. If we take a look at one of our finite modular successor structures, with this as the successor operation, notice that it's very close to already satisfying our axioms. It's closed under the successor operation. Every element has a predecessor, which is a little bit of a problem, but that's okay. We can add in a copy of omega as a secondary set of elements, and so now we have some elements and we have some other elements, and now there is one element that doesn't have a predecessor. The predecessor of any element that does have a predecessor in this structure is unique, and actually in this structure there are no loops of size 2 or 3. It's only when we get to the axiom that says that there are no loops of size 4 that we wind up seeing that this can't be a non-standard model of this structure. If we have a structure that satisfies these axioms, well, it necessarily has a smallest element and then successors of that. Now again, let's consider a maximal infinite set of points that are infinitely far from each other and infinitely far from 0. We can still make sense of this in the successor structure case. We'll call these elements Ci, and then for all of these elements, because they're not 0, they have to have both predecessors and successors. And those elements have to have predecessors and successors. And so this is what our non-standard models necessarily have to look like. They have to look like omega with some number of copies of the integers. I'm going to use L here because we've already used S, and so there's no real good letter here. But in this case, L is not a linear ordering. It's just an arbitrary set that represents the set of different z's that we wind up having. I guess I should mention, it's really important that there's no loops to make sure that these are all different elements, right? Because if it accidentally happened to be the case that C1 plus 2 was equal to C1 minus 1, then we'd have a loop here in these elements. And again, we're trying to avoid that. We want omega plus some number of copies of the integers, not some number of copies of the integers and some number of loops. And then finally, we've shown that all non-standard models have to look like this. But we haven't shown that everything that looks like this actually is a non-standard model, actually satisfies all of the same first-order logical formulas as the original structure. We've only shown that it satisfies the particular formulas that we wound up picking. So we need to do a little bit of work, and that work is exactly the same as last time. We need to play an Ehrenfeucht-Fraïssé game between this structure and the actual natural numbers. And again, if spoiler plays in either of these omega parts, super simple. The tricky thing is if spoiler plays in one of these integer parts, that duplicator has to match it to an element that's sufficiently large within the omega that they're playing against, and they can use this fact here in order to guide their choice of point to pick, so that everything is sufficiently far apart that for the purposes of the game of length n, it looks like the point that they match, this point 2, let's say, is infinitely far away from any other points that have already been previously matched. And again, they can only make it look really far away if they know how long the rest of the game is. Filling in the gaps of the proof is not particularly enlightening, but I hope I've given you a sense of enough to be able to fill in the gaps if you wanted to. But yet again, we have completely classified the non-standard models of this structure. We've done it thinking of this structure as a relationalized successor structure, but again, the non-standard models of relationalized successor structures are exactly the same as the non-standard models of the actual successor structures because the languages are essentially the same. It's just that we needed to do that relationalization in order to be able to use Ehrenfeucht-Fraïssé games and in order to make it a whole lot easier to do this induction. And we've also provided a complete axiomatization of this class of structures. It's just that in this case, that complete axiomatization is infinite. This is a very significant difference from the linear ordering case. In the linear ordering case, we had a finite number of axioms, and we could AND them together to actually just have one axiom. But here, we necessarily have a countable number of axioms. We can't AND together infinitely many things, so it's genuinely an infinite collection of axioms. Let's call our infinite collection of axioms AN. Now, suppose you come to me with a finite collection of axioms, so you claim, for this particular class of structures. And we'll AND together all of those axioms that you claim, because there's only finitely many in your claim, to a single axiom B. So just like how the various ANs are single formulas, we'll have B also be a single formula. So here's the thing. Any structure that satisfies all of the ANs necessarily has to satisfy B. Either way, we're describing the non-standard models of the natural numbers as a successor structure. Now, if you remember back to our compactness video, there's an exact relationship between structures existing and proofs, specifically proofs of consistency. But this exact relationship tells us that if whenever a structure satisfies a set of formulas, then it necessarily also satisfies another formula, then we actually have logical implication in the proof sense. Now here's the clever bit. Remember that any proof that uses an infinite number of hypotheses actually only uses a finite number of those hypotheses because the proof is finite. But here's the thing. Let's take a look at a structure that satisfies all of these formulas, but doesn't satisfy all of the ANs. So again, here we have a structure that consists of a copy of omega with its notion of successor. This is just to make sure that we can have an element that doesn't have a predecessor. And then a very large loop. It's actually, the size is just a little bit offset from M in order to account for the offset in the axiomatization. This structure here, for the right choice of N, satisfies all of the AN up to M, but it doesn't satisfy all of the AN because it has a loop in it, and one of the axioms says that there are no loops of this particular size. So we have this structure that satisfies this, and your claim was that from this we can prove B, we can prove our axiomatization. Well, if this was genuinely an axiomatization, then it would prove all of the facts that are true of this original structure, including all of the axioms, including the one that says that there's no loop of this particular size. So we have a contradiction. We cannot have a finite set of axioms that axiomatize this particular structure here. So we've been very successful taking our structure that has an operation on it and turning that into a relation, and then using Ehrenfeucht-Fraïssé games in order to study that. And that's the typical way of applying Ehrenfeucht-Fraïssé games to study structures with operations on them. But here's the thing, it's completely thrown off our quantifier counts. Analyzing EF games on a corresponding relationalized structure can't tell us anything about what sorts of formulas are available at any one particular quantifier depth within the original structure. And there are some fun and exciting results out there about what sorts of things we can say with only so many quantifiers. So what happens if we don't do this translation? What happens if we allow atomic formulas within our logic of the form a whole bunch of successors applied to x is equal to a whole bunch of successors applied to y? What happens if we allow these sorts of formulas to be atomic formulas? Well, let's play an Ehrenfeucht-Fraïssé game. We'll let M be the natural numbers with successor, and we'll let N be the natural numbers followed by a copy of the integers. This is a basic woozle for L equals 1, with the typical notion of successor on that woozle. Now, we've already seen that this is a non-standard model of this structure. we saw that any formula that was true in this structure as a relationalized successor structure was also true in this structure, and vice versa. And because the relationalized successor structure language is expressively equivalent to the actual successor language, we know that any formula that we could write here in the actual successor language is also true of this structure here, and vice versa. It should be the case that for any n, duplicator wins the EF game of length n between these two structures. However, let's say spoiler plays here at 0, and duplicator wisely matches it to 0. Of course, if duplicator matched it to something else, then spoiler would have a different winning strategy. So duplicator really has to match 0 to 0. And now, suppose that spoiler plays at c, some arbitrary element of the z part of n. Then what can duplicator match it to? Well, suppose the duplicator matches it to, I don't know, 5. They're going to match it to some finite number. The game is lost at this point, because there's an atomic formula that's true of these x's, but not true of the corresponding y's. x2 is the 5 times successor of x1. This is an atomic formula, but that's not true of y2. And regardless of which point duplicator matches the C2, there's always going to be some atomic formula that looks a lot like this, distinguishing the two structures. So duplicator has lost in 2 turns. That wasn't what we were expecting at all. We know that these two structures are logically equivalent to each other, and yet somehow spoiler is still exploiting some kind of difference between the two structures. And to figure out what's going on, it might help to look at the specific difference that spoiler is exploiting. Let's actually pretend that this connection here happened because these structures have extra constants representing 0, just so that we can focus on this specific turn here. Spoiler is exploiting the fact that in this top structure, every element is some number of successors applied to 0. Right? X equals 0, or x is the successor of 0, or x is the successor of the successor of 0, or so on and so forth. Whereas in the bottom structure, spoiler is exploiting the fact that there exists an element which is none of these. And so we see that the difference that spoiler is exploiting between these two structures has an infinite or in it, or an infinite and. We know that there's no finite logical formula distinguishing these two structures, but somehow this Ehrenfeucht-Fraïssé game is capturing this infinite difference between these two structures. And I find this profoundly disappointing. When I was introduced to Ehrenfeucht-Fraïssé games, I was told that they correspond exactly to first-order logic. But as we can see here, that's not quite the case. Ehrenfeucht-Fraïssé games correspond to an expanded logic where you're allowed to take infinite ands and infinite ors, provided that there's bounded quantifier depth within each of these formulas. So again, we still have to talk about Ehrenfeucht-Fraïssé games of length n, and we want to restrict the quantifier depth of each formula. And actually, if we have infinite ands and infinite ors, you could like and together or together a formula of quantifier depth 1 and a formula of quantifier depth 2 and a formula of quantifier depth 3 and so on and so forth, and get a formula of unbounded quantifier depth. We don't want that. Ehrenfeucht-Fraïssé games, we still want them to be finite, we still want them to be n turns long, and so we're going to restrict it that when you and together or together infinitely many formulas, there's some bound on the quantifier depth, so that we can work out what the quantifier depth of the whole formula is, and so we can therefore talk about the game taking a finite number of turns. It just so happens that in the case of structures that have no operations and only finitely many relations, having the ability to and or together infinitely many formulas of a particular quantifier depth doesn't actually help you. It doesn't expand the set of things that you can talk about, because there are only finitely many formulas up to logical equivalence of any particular quantifier depth. If you want to think about this in terms of the Ehrenfeucht-Fraïssé games, remember that ands and ors correspond to duplicator making a choice. In this case, duplicator is just making the choice of how they want to lose. They don't get to choose a winning move. All of these moves, all of these things that they could match C to will cause them to lose, but they get to choose what sort of atomic formula they lose on. And that's still a choice that they get to make, and they have infinitely many distinct choices that they could make in this particular game. The claim is, when we're working with structures with only finitely many relations to them, there's only finitely many really distinct choices that duplicator can make at any one time. It's a little bit tricky to prove, but it's an inductive proof that starts with the fact that there are only finitely many distinct atomic formulas. And of course, in this structure here, right, when we're thinking about the natural numbers with an actual successor operation, there are infinitely many logically distinct atomic formulas. So how can we fix this? Again, we would still like to be able to reason about logical differences between these structures and be able to still capture quantifier depth of those logical differences. Well, suppose that we have our two structures and there actually is some logical difference between the two structures. We have some sort of formula phi that's true of M and not phi is true of N. And we would like to identify this as happening. We would like it to be the case that Spoiler wins a particular Ehrenfeucht-Fraïssé game because they're exploiting this difference. Well, here's the thing. This difference, this formula phi here and the corresponding formula not phi, are only going to contain finitely many different sorts of atomic formulas. Specifically, if we're talking about successor structures, there's going to be a limit on the number of times the successor operation is applied to itself, is nested within these formulas here. And so we're going to modify the Ehrenfeucht-Fraïssé game ever so slightly. At the beginning of the game, Spoiler specifies a finite set of atomic formulas, and those are the only sorts of differences that can end the game for duplicator. So at the beginning of this game here, Spoiler specifies some sort of n, and we say that duplicator loses if there's some sort of formula of the form the successor applied less than or equal to n times of x is equal to the successor applied less than or equal to n times to y. Right? This is a finite number of atomic formulas are of this form. But if it's the case that there's some sort of atomic formula with more than n successors nested like this, duplicator doesn't lose if there's some sort of atomic formula like that distinguishing the two structures. And so based on the size of the nesting, when we actually play this Ehrenfeucht-Fraïssé game, duplicator can match this C to some really large finite number. The larger the nesting, the larger this finite number is going to have to be. But duplicator can do the matching in order to be able to win this game of length n for any n. And this is exactly the same sort of structure that you would want to use if you wanted to deal with Ehrenfeucht-Fraïssé games on structures that have an infinite number of relations to them. At the beginning of the game, Spoiler would specify a finite subset of those relations that they hope will show up in this formula that distinguishes those two structures, and then Spoiler and duplicator play the game where they only are allowed access to that finite number of relations. Spoiler is perfectly happy because they're still allowed to exploit this difference between these two structures. Some sort of first-order logical difference is only going to have finitely many relations to it, and so Spoiler just picks that set of relations. And duplicator's perfectly happy because they can adjust their strategy based on the set of finite relations in a way that they maybe couldn't if there were infinitely many relations that they were trying to avoid be satisfied. So, as we've seen, Ehrenfeucht-Fraïssé games are an extremely powerful tool, but they're really only designed to work with structures that have a finite number of relations to them and no operations. In this video, we've seen a couple of ways of trying to salvage that in order to be able to study structures that have either operations to them or infinitely many relations. This is tricky because Ehrenfeucht-Fraïssé games actually exploit differences between structures, not quite first-order logical differences between structures, but actually differences in a slightly expanded logic that has infinite ands and infinite ors. Ehrenfeucht-Fraïssé games are also limited by our intuitions for playing games. We've seen that in the case of linear orderings or successor structures, or this is even true for finite graphs, playing Ehrenfeucht-Fraïssé games can actually be pretty intuitive, and that allows us to make some really intuitive observations and then prove those observations by making our intuition formal. However, there are some structures, such as what happens if we're interested in the natural numbers with addition, where our intuition for playing games starts to break down, and maybe there are some other tools that are more effective at reasoning about these particular logics. In the next few videos, I'll talk about some other tools that we can apply in order to analyze these logics, and we'll focus on analyzing the natural numbers with addition, that is to say, Pressburger arithmetic. So thanks for watching this video. Please leave a comment down below if you have any questions or comments, and I hope to see you in the next video.